Hello everyone, I hope you guys are doing well. So in this video, we're going to talk about the paper Stable Diffusion Reference Only, where it takes two images as input, an image prompt and a blueprint image, and generates a secondary painting. So what do I mean by all of this? Let us look at this specific example. So the idea here is that it takes an image prompt, which tells the concept of how it needs to look like, the color of how the output needs to look like. And then there is a blueprint, kind of like a conditional generation that you have for control net, where you have some kind of map. In this case, it's an edge map, and the output generated needs to respect this edge map. So these two are the inputs and this is the output. So the first image gives us the concept, the second image gives us the structure of how the output should look like, which in this paper they refer to as the blueprint image, and it needs to generate the output that looks pretty much like the initial image. So that is the task, and let us get into the paper. So Stable Diffusion and ControlNet have excellent results, but they're hard to use due to their granularity and the method of control. So specifically, what do they mean by that? So let us remind ourselves of the Stable Diffusion architecture. Specifically, what the Stable Diffusion architecture does is it takes two inputs, it takes a noise image, it takes a text prompt, and it combines the text into the noise through a cross attention mechanism, and it keeps doing this repeatedly through a unit, and what we get is the generated output. And ControlNet acts like an add-on model to Stable Diffusion. So you can imagine ControlNet as being something like this, and what ControlNet takes as input is the structure of the output. So by structure, it can be the edge image, depth map, segmentation map, and so on. So what ControlNet ensures is that the output that we have generated respects the structure that we give here. So with respect to Stable Diffusion and ControlNet, generally this path is pretty good. So you can get outputs that that are controlled by these inputs quite well. But the issue with this architecture is that if you want the output to be a specific concept, let's say a face of a specific person, and it is hard to give that information. If you want to have a person in a new pose, the issue is that you can specify the new pose here. However, how do you give the concept information, right? You're limited to give that information through text, and that really limits the power and control that you have on these models. So let's continue reading the paper. So this cannot be used very well where the primary task is secondary painting. So what do we mean by secondary painting is basically this task. So you have a primary painting and you want to generate another painting of the same concept in a slightly different context. It could be a different pose, it could be like slightly moved limbs, it could be a different expression, and so on. So the issue is this task is currently not solved with Stable Diffusion and ControlNet, and this paper proposes an alternative way to solve the task. Though one way to solve it with Stable Diffusion and ControlNet is if you're allowed to fine-tune your model to learn a specific concept using textual inversion or dream booth. But yeah, it can be complicated and expensive. So this paper proposes an images to image model that uses two types of conditional images for controlling. The first type is the conditional image, which is the image prompt that gives the concept and color information. And the second is a blueprint image that controls the structure of the generated image. In the way these people do it is they natively embed all of this information into the unit, eliminating the need for an external control net module. So essentially, instead of doing something like this, these people's architecture, the authors that they propose here, is stable diffusion reference only. And what it takes as input is, instead of text, it takes two images. So it takes the image prompt and it takes the blueprint image. And what it generates is a secondary painting of the image prompt that respects the blueprint image. So that is the idea behind this paper. So let's continue reading. So secondary painting primarily involves modification, association, and derivation based on a given concept. This is a common task, especially if you want to draw new poses for a specific character, for example in comics, or in animations where you need a very high frame rate, and doing this can get repetitive and workload heavy. So currently people try to solve it. People haven't tackled this specific problem, but one way to solve this would be to use stable diffusion and control net. But the problem with using this is that you cannot give a primary image. You have to give a text as input, which is a problem because all of this, it's hard to encode all of this specific information about how the face is like, how the eyes is like, the shirt, the wrinkles, everything into just one text prompt, given that each text prompt only has like 77 tokens. So what is the standard way around this? So if we think about this more closely, let's get into the stable diffusion architecture. So let me draw this for you. So I'm essentially drawing the unit of stable diffusion here. And this is how the unit looks like, right? You have a bunch of ResNet blocks and then you have skip connections. And this is what will repeatedly denoise your input image. So if you remember the architecture, what is on this architecture towards the end is there is a cross attention layer at the end of each of these. So this cross attention layer is where your clip text embeddings go in. So if you imagine all of these cross attention layers getting the same input, and that input typically it goes from clip. So you take the text as input and then you get the clip embeddings and then you feed it to the cross attention layer. So one way to work around this, especially if you want to feed images, is so this is option 1. So option 2 is you can still use clip but use the clip image encoder and then give an image as input and then feed this in. So if you remember, clip kind of has a common embedding for the text and image space. So especially if you have, like, let's say a person going on a sailboat in the water with mountains in the background, the way clip would describe this image is, or the way we describe this image is, mountains in the background, very naturalistic image, a person on the sailboat going in water. So that is essentially the semantic information of this image, and that is what clip embeds. So clip embeds both that semantic information, mountains in the background, sailboat, man on the sailboat, that context. When it's encoded as the text, the embedding you get from it would be quite similar to the embedding when you feed in this image. So the idea here is, when you use the clip embeddings, what you have here is the semantic information of the image. But the problem is, this kind of rough semantic information might not be good enough for a task like this. For example, if so the text description of some image like this would be like anime style girl with nice hair and some flowers near her ears that look like a fox, right? So that is all the information uh, this can encode. The problem is that that encoding might not be good enough because we want to know a much clear picture of what the input actually is, because there is a lot more detail here that cannot be described in just 77 tokens of text, and that is the limitation of clip. So if we get back to the paper, so there have been recent works to get around this. There's the control net reference only and IP adapter, but the issue is that generalization to new characters is just not good. So let's briefly take a look at the IP adapter paper so I can tell you a little more about what goes on there. So yeah, if you remember, the issue is that we are unable to generate specific concepts using stable diffusion because we take the text as input. And the way IP adapter handles it is it uses an additional cross attention layer that goes along with your text embeddings cross attention layer. So essentially what's happening here is that you have a frozen image encoder and then you use that to do cross attention. So what happens is that the output that is generated, it doesn't only respect your input text prompt, but it will also respect your input image. And that was the primary idea behind this paper. And yeah, this paper doesn't work too well, and the authors also mention a little bit more about it. So specifically they say that existing methods that have text have less precise control, and the methods that have images don't do good as well, specifically because the probability distribution of the generated images is limited by the text to image model. So what do they mean by that is, specifically in this case, if you see stable diffusion, what is happening during this training process is that the text to image model is frozen. They use the pre-trained weights. They only modify the image encoder weights. And the authors argue that the problem with this kind of approach is specifically that if you think of your text to stable diffusion, and let's say this is your text embedding, and the same text can generate a bunch of images based on your conditioned noise, right? So this is the probability distribution that stable diffusion learns during training, but during training it never sees an image of a specific character exactly like this one. So the issue might be that to generate an image that looks like a very specific character that is not in its training distribution, it might have to generate something here. So the text needs to be able to generate something here, but even if you control your attention in specific ways like in this paper, it might be hard to go out of the training distribution, and that might be the limitation of this approach. So the authors propose an approach to specifically address this limitation. So if we continue reading the paper, they say that these text aligned features are too rough to be general enough. And what this would essentially need is modifying how training happens, and that you need a completely new architecture to solve this problem. And this paper proposes stable diffusion reference only, which is a model where the first input is an image prompt that tells you the conceptual and color information needed to generate the image. And the second image is a blueprint image, which tells you the visual structure of the generated image. And with the basic structure of the network, they still use stable diffusion and the VAE that is in stable diffusion. So if you remember, the VAE, where it comes from is that stable diffusion, all the processing, all the denoising that happens in the unit, it does not happen at full resolution. If your generation is 512 by 512, all of this processing happens at 64 by 64, and the VAE encoder is used to go down to 64 by 64, and the VAE decoder is what is used to go back up. So these authors of the paper are continuing to use those the same VAE and the basic structure of Stable Diffusion. Specifically, the authors use a VIT to encode the image prompt, and they apply it to the unit backbone via cross attention mechanism. So if you remember our previous diagram here, so we had the issue that if we were using clip embeddings, the semantic information of the image is not encoded well. So the authors say that let's not use clip, let's use a vision transformer and take the image and then use the vision transformer embeddings here. So the advantage here is that this is not limited to semantic information. This would encode the color and concept of the original image, but not just the semantic information. And that is what is needed to solve this task. So that's their primary proposal. And the way they handle the second input is by adding a blueprint input to the original unit. Specifically, they add a simple convolutional network to affect the Q matrix of the cross-attention mechanism. So the idea here is that the blueprint input and the image prompt control how the generation happens through the cross-attention mechanism. And how do they get their training data for this? So they have a bunch of a big data set of images, and the way they identify similar image pairs is by using clip. And then they use these similar image pairs for training of the model. So let's get a little more into the details of the algorithm so that we understand the architecture better. So what you essentially see here is that your blueprint image, you generate some features from the blueprint image, and those features are what are being used to control your queries, right? So if you see, the image encoder tau theta is used to extract the concept information, and that concept information changes your values and keys. So these values and keys are controlled by the concept information. And how about the queries? The queries are controlled by the blueprint image. So the idea specifically here is that this is intuitive because each patch of image would look at the image prompt to see how it should be colored. So this details that we have tell us how the image needs to be colored, and the query, this gives us information as to how the output structure should be like. And then they use an L2 loss to learn this model. And if you see, they do have decent results, and it was quite impressive. In this paper, they only train it on the anime dataset, so we still don't yet know how hard it is to make this generalized to a diverse set of images. So it would be really interesting to see future work in this space. And that is all from me. I think I can go a little bit into the experimental details as well so that you get an idea of how much compute this takes. So they use 4 A100s, start training at a resolution of 256 by 256 for 100,000 steps, and then they reduce the batch size, increase the generation size, and train it for more steps. And then they finally fine-tune it on a much higher resolution. So this is very similar to the Stable Diffusion training protocol, and they reuse that pipeline as much as possible, and that seems to work quite well for them. And another thing here is that they also try to reuse the pre-trained weights as much as possible, and that is another reason why they're able to get away with using just 4 A100s. So that is all from my end. I hope you found this video educational and learned a few new things. Thank you for your time.